Okay, welcome back everyone. In this video, I'm going to show you why you should actually believe the mirror equation that 1 over f equals 1 over do plus 1 over di. Now I'm not going to prove the equation, but I'm at least going to show you how to determine where an image is without using it. Okay, so when we ray trace for mirrors, there's three so-called principal rays that we should always use in a diagram. And just to be clear, these principal rays always come from the same point on the object, and so that allows us to locate, if we draw carefully enough, that same point on the image. Okay? So I'm going to describe the principal rays and then show you how they're used. So principal ray number 1 is a ray that is incoming, or incident if you like, parallel to the optic axis. This ray is reflected back through the focal point. And let's just do this very quickly for a concave mirror. So here's my concave mirror, and so what I have to do is to basically label where my focal point is. Okay, and I have an image perhaps out here, and to try to be a little bit more accurate, we're going to move the picture a bit so that I can access my rays. Okay, so I'm going to do this first ray, and it's a ray that is incoming, so it starts here. Oh, that doesn't look like a ray. It's incoming parallel to the optic axis, kind of like that. Now, at this point, what I have to do is zoom in. That's way zoomed in. And take a look at my diagram and construct the normal to the surface at that point. Okay? Now, one hint for constructing the normal is if I claim that the focus is right here, then twice that should be the center or the radius, and the normal should go pretty much through that. Okay? And I can apply the law of reflection, which says that theta incident will be equal to approximately theta reflected, and so if I do a new ray, it will start here and it will travel through the focus. Okay, so it's not perfect, but you can kind of get the gist of what's going on here. That is the first principal ray. Let me move things back. The second principal ray is basically the reverse of this. Okay? It is a ray that passes through the focus. Okay? So it will be reflected back parallel to the optic axis. And this is just taking number 1 and doing it in reverse. Okay? So I'll pick a different color. Let's do green and get a ray going. So now I start at the same place and I go through the focus, and that's pretty close. Okay? And so now what I do is I construct my normal, and I hope you'll forgive me if I just do this kind of, well, I have to go from the center, right? So there's my normal, and I know that I'm going to, well, I'm going to zoom in so I can show you this. Okay, and so what I know is that the incident ray will have the same angle as the reflected ray, and so I'm going to end up reflecting back parallel. Okay, so these are the first two principal rays, and this is going to work out fairly decent for us because we see that they are already converging, and that's what happens with a concave mirror if the object distance is greater or outside of the focus. Okay, so what I could do is I could put a dot right here, and that would be the tip of the arrow on my image. So if this is the object, I have located the image, and if this distance right here represents the object distance, then I can measure or calculate the image distance. Okay? And I'm just going to toss some numbers onto the mirror equation. Let's say for fun that, well, let me zoom out again. Let's say for funsies that f is plus 5 centimeters because it is a concave or converging mirror. Let's say that DO is plus 15 centimeters. Why? I'm just making easy numbers. Let's find DI. Okay? So this is like a easy practice problem. So 1 over f equals 1 over DO plus 1 over DI. Okay? So 1 over 5 equals 1 over 15 plus 1 over DI. Notice that I have a positive 5 and a positive 15. Those are both very important. Okay, well I need to make that 15, so basically what I get is 2 over 15 is equal to 1 over DI. And just like the electricity unit where we had to flip to find the total resistance, don't forget to flip this so that DI is actually 15 over 2 or 7.5 centimeters. Okay? So now if you look at the diagram, does it look like DI could be approximately 7.5 if DO was 15? Sure, that's reasonable. Now it's not going to be perfect because DO should probably be more like over here, but you definitely get the idea. Okay? And DI is positive, which is what we expect for a concave mirror. We get a real image, and notice that it is on the same side of the mirror as the object. Also notice that it's upside down, it's inverted, and it's a little bit smaller. We can calculate the magnification, but we have more to talk about. Okay? So let's get back to the principal rays. I'm just going to show you that this third one works. The third principal ray is called the chief or radial ray. And ignore all that. Basically, this ray goes through C, the center of the mirror, and is reflected back through C. And again, this is because of the geometry. If this is a sphere, then the center also represents the radius. Okay? Now the center here should actually be more over. Okay, but you get the idea. I'll do this in a third color. Well, we'll do black for this one. So that means that a ray that starts at the tip of the object that goes through the center, kind of sort of like this, is going to hit the mirror. And I didn't draw the mirror long enough, but you get the idea. It's going to hit the mirror and then bounce back, and lo and behold, it also intersects in the exact same place. Okay? So there's the three principal rays. Now I'll do a fourth, and this fourth principal ray, I'm running out of colors. Let's change the color of the pen right now to a lovely purple or violet. Okay? And this fourth one is something that strikes the vertex. And there's nothing too special about this, but you can strike the vertex kind of like so, and then you just apply the law of reflection. So this angle right here will be equal to this angle, and so I just kind of go like so. And again, whoops, sorry about that. Again, we are intersecting at the same point. So these are four rays. Really, in order to determine where an image is, you only need two of these rays. Okay, now very quickly, I'd like to show you how this works for a convex mirror, because it's a little bit different. The principle is the same, but it's wacky. Okay, now, I kind of like this purple, so I'm going to stick with it. So here is an optic axis, and here is a convex mirror. Okay? So this is going to be diverging. So again, let's have an an object right here, and a convex mirror has a negative focal length, so that means that the focus is on the opposite side. Okay? So no light actually comes over to this zone on the right of the mirror. No light actually reaches because it's bouncing off the mirror. Okay? So now, I guess I'll go back to blue. Let's do principal ray number 1, which is something that goes in parallel. Okay, so here we go. It goes in parallel and it strikes the mirror, and we have a problem. Okay? The problem is it's going to bounce off the mirror and it can't possibly go through the focus. Now instead what's going to happen is it's going to look like it came from the focus. Okay? So what I'm going to do is well, first of all, I'm putting the center in here so that I can show you what the normal would look like, something kind of like so. And then the law of reflection will be obeyed, so I have my two angles, and the actual ray of light will travel off something kind of like, maybe like this. That's what the actual ray of light will do. But what this does is it seems like it came from the focus. So that's what happens with principal ray number 1. Okay, now the opposite of this, principal ray number 2, is the one that goes through the focus. So let me change to a different color, to red, and wait a second, I can't go through the focus. Why? Because the mirror's in the way. So the light ray is going to make it to the mirror, and then it will reflect. And when it reflects back parallel to the optic axis. So something kind of sort of like this. Okay, now that's a problem because I have two light rays which have bounced off the mirror, but these are diverging from each other. That's a problem. Well, I need to do the same thing with this second ray that I did for the first, and that is I need to extend the reflected ray backwards. Now this is the tricky part because you have to be careful that you extend the reflected ray backwards, not the incident ray, but the reflected one. That's key. If you don't do that, it's not going to work. And if I extend it backwards, get a little bit of a zoom in here, okay, I actually get a place where these cross. And this is where my image is going to be formed, right here. So that's my image. And there's a couple of things that we have to be aware of for these images. Okay, so for a convex mirror, remember that DI will be negative. Okay, can I prove that? Well, sure. Let's put some numbers on this. Okay, let's say that the object distance is positive 15 centimeters because object distances are always positive. Let's say that the focal point is negative 5 centimeters. Remember, why is it negative? Because we have a convex mirror. Okay, and now let's use the mirror equation. So 1 over F equals 1 over DO plus 1 over DI. Okay, so negative 1 over 5 equals 1 over 15, which is positive, plus 1 over DI. I still need a common denominator, but now it's negative 3. So I get negative 3 minus 1 is negative 4/15 is 1 over DI. So the image distance is negative 15/4. That's like negative 3.75. Okay? Now you can see in my diagram, hopefully you can see that if this distance is negative 3.75, well, that makes sense if this distance is about negative 5. It's kind of on the same scale, right? Thus proving that for a convex mirror, you get a virtual image. Notice that so first of all, it's virtual because di is negative, and it's upright, and convex mirrors make for reduced image size. Okay? Now the last example that I need to do is for a real image. I need to do a concave mirror that is a virtual image. And I'm going to save that for the example problem. Okay? So I know this video was a bit long, but knowing how to do these ray diagrams is extremely important, and you can also use this when we do lenses.